There we go.
Okay. Yeah, we see you now.
Okay, good. Forward. Record. Okay. That's backed up. It's recording. Sheesh.
And these are the ones over here. Look at me.
Okay, well, this is better anyway. It's not going to be optimal, but
Make it bigger.
okay. Well, yeah. So I kind of filled the frames with that. You're not on camera.
It's probably for the best.
Okay, well, let's get started. So today, Ryan is going to describe the Sage server and how you go get your homeworks and how you do your solutions. And I talked about this a little bit at the end of last Tuesday's lecture.
How much time am I supposed to spend?
Oh, well, okay, so I think maybe the thing to do is go through how to use Sage, point out where they get tutorials, go through homework 1, show where the helper code is, and then any other things you like to do. Well, no, I mean, maybe you already planned some things, so that would be fine too. So I didn't plan anything. Well, okay, the goal is to make it clear how to get to the homework.
Sure.
And like I said before, this Sage system, which hopefully, okay, first order of business, you should all have accounts. You should have gotten, if you're enrolled, you should have gotten an email that says, this is your account, and you should have logged in. Then hopefully you took my advice last time and went to the Sage homepage and kind of worked through their tutorial. You may have to go back a couple times, but and then they've got a server up there, they'll give you a fake account, you can go through that. Or you can try doing, the tutorial on the local campus server if you want, your choice. So as of today, their homework 1 assignment is up there, and you'll see 3 worksheets when you log in and click on the published area. So the published area is where we all share things. Typically, I'll put the homeworks up there, but you'll also, the assignments, with a statement of what the problem is and then some cells where you can add code. You can also add more documentation, add LaTeX mathematics, and add more code cells for each thing. Then you'll also see another homework, at least for the first few that have, let's say, homework N, homework 1, helper code. We put in some extra things like high-level function that helps you plot vector fields, or phase clickers, things like that. So you don't have to do the low-level plotting programming. You just kind of plug in the equations and give the range, and then you can kind of explore around in the phase plane where the orbits are going, for example, in that case. But don't hesitate to ask us questions. I mean, there are a lot of particular things, which Ryan will go over about how to use Sage. Not so different in overall workflow from MATLAB or Mathematica notebook, but there are differences too. So, okay, so Ryan, take it away.
Okay, so the first thing that's tricky, and you can't really see it here, but if you just go to campy.csc.ucdavis.edu, you'll get this, which is not what you want. The important thing, and it's linked correctly on the course website, is it's HTTPS. So secure HTTP. That will take you to the correct location. So if you go to the wrong place, it's because you're doing normal HTTP, not secure. And then just put in the username and password that were emailed to you. Click sign in. And you should be greeted with something without all these notebooks. And the first thing you want to do is go to settings and change your password, because the one I sent you was just 10 random characters that the computer generated, and if you ever forget it or whatever, you'll have to go back and find it in your email. Easier to send it to something you vaguely remember. After that, you can go to published, and so far there are 3 published worksheets. We'll go over this one right now. This is a description of all the problems for homework 1, And this is the exact same worksheet as this, but with additional helper codes like Jim was saying, the code that will plot vector fields for you and stuff like that. So you'll probably want to choose this one and run through that. But anyway, so you click on one of these worksheets and it gives you a static version of it. You can see what's going on here. And you're going to click edit this in the upper left corner. Or it might say edit a copy or something similar. When you click on that, it makes a copy of it for you to use in Sage right here. This will be your local copy. And it should look essentially the same. And page through it. It's got text areas.
A little slower.
Oh, I was just getting to some random point. There's text areas, and then there's code areas. These are code areas. And the text areas, you don't need to modify, but if you did want to, for whatever reason, you just double click on them. And it gives you this little editing block. So starting at the beginning, this lab here walks through one problem from Strogat's textbook, example 611, which is to analyze this system of differential equations. X dot equals x plus e to the minus y, and y dot equals minus y. So the first thing we want to do is calculate the null quantities, which, if you recall, are where the derivatives are 0. The x null client is where the x derivative is 0, the y null client is where the y derivative is 0, and so on. So to get started, does anyone know Python? So the first thing you want to do, and this is something you have to do in many computer algebra systems, is define variables. So right now we want x and y to be variables that Sage knows are mathematical variable objects that you can put into functions and such. So rather than be over here, this x and this y are Python variables, and because they're assigned using this function here, Sage knows that these Python variables act like mathematical variables. So we want x and y to do that, and then we define dx and dy as these expressions we saw. So we say dx equals x plus the exponential of minus y, and dy equals negative y. And we can evaluate that. So when code block has a red bar next to it, which you might be able to see, that means it hasn't been evaluated yet. When there isn't a red bar, it has been evaluated. And if it has a green bar next to it, that means it's currently being evaluated. You won't see that too often because most of these blocks finish executing in a fraction of a second. But if you have something that takes longer, for example, also, if you want to add a code cell, if you hover between two areas, you'll get this blue bar. If you click on it, you get a code cell. And if you hold down Shift and click on it, hold down Shift and click on it, you get a text cell. So that's how you can add text or code to an array. So for example, if something is executing, I'm just telling the computer to sleep for 5 seconds. You can see there's this green thing right here, and that means it's currently executing. And then it disappears when it's done. Okay. So we've got these x dot and y dot expressions, and we want to calculate the null clients. So what we're going to do is we're going to use Sage's built-in solve method to solve for where dx equals 0. We're going to solve for that as a function of y, and so we get this. We're going to call the output of that x null clients. So x null clients is going to be the solution to dx equals 0. And notice we use 2 equal signs here, and we use 1 equal sign here. So for those who don't know, 1 equal sign is used for assigning a value to a variable. 2 equal signs is used for stating that 2 things are identical. So this is saying we want dx to be identical to 0, and this is saying I want to set the variable x null clients equal to the solution of this. So, and then I'll do the exact same thing for the y null clients. I'll set where dy equals 0, And then I'm going to print out the solutions to both of those. So I'll print out dx equals 0, colon, and then the solutions to that. And dy equals 0, and then the solutions to that. So we execute that. And here we go. We have that when y equals 0, dy is 0, which we can see from the equation here. Y equals 0 is the only solution to this that will set dy equals 0. And the solutions to x dot being 0 are when y is equal to the log of minus 1 over x. Okay, so we can plot those, and there's a link here to the documentation for the plotting function. We're actually using a different plotting function.
You may not tell me which one.
This is the Sage plotting function.
What is Sage?
Okay, so we're going to do two plots. The first one is of the first null line, and the second one is of the second null line. So we're going to plot log of minus 1 over x, and we want to plot that from x equals -2 to 0. And we're going to give the line a thickness of 3. It just means it's nice and thick, visible. And then for the second one, we're going to plot it, the function is 0. We want it plotted from -2 to 1. And it's also going to have a thickness of 3. We're going to set the color equal to red. Then we want to put them both on the same plot, so we add them together. And then we tell the computer to show the two plots. So we do it. And we get our plot with the null lines here, which normally would, if we had a higher resolution projector and they didn't have this blown up so large, it would all fit nicely on your screen. So we see the blue one is our x null line. That's the log of -1 over x. And the red one is our y null line, and that was x equals 0, or y equals 0. And the reason we didn't plot this beyond 0 is because it's not defined yet.
So, and note that where the null lines cross, you have a fixed point, right? Because both x dot and y dot are 0. So this is kind of a graphical way to see where they are.
So x equals -1, y equals 0, we should have a fixed point. And we can verify this by plotting the vector field. And we've given you a little function here called plot vector field. Or Sage has, I don't recall which.
That's an SSH one.
Okay. And you have to give it three things. First, you give it the system of equations to plot. So the x part and the y part. And we have to group those together with parentheses. This is the first argument to the function. The second one is the first variable. We want x, and it goes from a -2 to 1. And then we plot y, and y is going to go from -1 to 1. So it should have essentially this, well, it should go as high as this on the y dimension, and about down to here. And it will go from -2 over to 1. So we can execute that. And we get a vector field. And we can see our null lines. So right over along here, we see that the arrows are pointed straight down. So that's where dx is equal to 0, because all the change is in the y direction. So along here, you can at least believe that dx equals 0. And down in this area somewhere, so that's that log of -1 over x. And right along here, you notice that above the axis, the arrows are slanted downward somewhat. And below the axis, they're slanted upward somewhat. So right at the axis, they have dy equals 0. And we can either use our imagination or a little function called phase portrait, which behaves similar to plot vector field, but it will actually draw trajectories. So the first argument is the exact same argument we give to plot vector fields. It's the x and y components of our field. And then we tell it what variables within those things are varying. So remember, dx and dy are defined in terms of these variables x and y, right here. And we need to tell the function that those are the ones we want varied. And we want the first one varied from -2 to 1, and and the second one varied from -1 to 1. We're going to plot 100 trajectories. I think this means integrate them for 2 seconds, or the equivalent computer time of 2 seconds. And we don't want it plotted in a polar field, because these are Euclidean dimensions, not polar. But some of your homeworks might require plotting the phase portrait of a vector or of a polar vector field, and so you would want to set polar equal true for those ones. So we can evaluate this, and here we go. So we started with a number of little initial conditions that then integrate outward, and we get our phase portrait here. Not too much to say about it other than that.
Let's see what the fixed point is.
The fixed point is right here.
You can kind of visually see it's hyperbolic.
Oh, yeah. There's the hyperbolic behavior going on. So then just some random odds and ends that are useful. So again, just to be self-contained, we can define x and y as variables again. And set f equal to x squared plus 1 over y, just some arbitrary function. And we can differentiate f with respect to x and differentiate x with respect to y and see what those are. Symbolically evaluate them. Sometimes that'll be useful. We can also integrate them. So integrating with respect to x and integrating with respect to y. So you just do your basic calculus.
Is integral f comma x synonymous or just is, I guess the different question is f dot integral sub x just syntactic sugar? I mean, can you can, are they just
Find out. So what you can do is put a question mark at the end of a function without calling it, and it will give you the documentation for it. So
yeah, so it is, right? They're just synonymous. But it's just the same way of calling the function. It's just syntactic sugar. Two ways calls the function.
You can do it either as a method call or as a built-in function. And you notice you can give it optional parameters to do a definite integral or leave them off to do an indefinite integral. Okay. So we can evaluate one of these integrals at a point, or the function at a point, by doing this. So f of 2 comma y, so we're not substituting in for y. We just tell it x equals 2. Similarly for y, and we can evaluate derivatives at, say, x equals 1, y equals 1, by substituting both values in, and so on. So we get those values. We can solve functions, or systems of equations. So we can solve for f, which is, again, x squared plus 1 over y. Find where it's equal to its derivative as a function of y, equal to this location. We can solve where f equals 1 as a function of x. Plot those things in a similar fashion. Plots. So it's a fairly flexible and useful just computer algebra and calculus system that you have at your disposal, which will be very useful for at least the first half of the class, analyzing these differential equations and such. Being able to, you can construct the Jacobian of a system pretty easily just by calling derivative. You can plot solutions by using this plot function. And if you're already familiar with matplotlib, that's available. The only trick is that you have to save the image to get it to display. So does anyone know NumPy and matplotlib already? Do you want me to show how to use it?
Yes, sure.
Okay, so for those who don't know, you can, rather than defining variables, we define arrays that we'll treat as variables. So x will be.
Well, maybe there's a slightly more general comment to make. I would say that Sage overall system is a little bit confusing because it provides some functionality, and then Python, which you can code things in, also provides its own libraries. So sometimes there's a little bit of confusion like we just saw before. I was confused as to which plotting function, whether it's the Sage provided plot function or down inside the Python package, that plot lib, there's something called plot. So there's a little bit of context dependent. So what Ryan is showing you is how to use the Python package, that plot lib.
Yes. So the first thing, I'm going to define a variable x, which is really just an array with values between 0 and 2 pi. And there's going to be 2 to the 10 different values in there. So we're going to arrange 1,024 values linearly spaced between 0 and 2 pi, and call that x. So we can see x is equal to, has this value and so on, all the way up to 2 pi. And we can set y equal the sine of x, and we can use matplotlib, which is alias as plt, to plot x and y. And you notice it doesn't do anything. To get it to show up in the web server, you have to save it. So you have to type save big and give it some kind of name, like this. And now it shows up. There's the sign of x between 0 and 2 pi. So if you're familiar with matplotlib, or you find some kind of tutorial online and want to use NumPy and matplotlib to do a calculation, the one thing to really remember is that to get matplotlib images to show, you have to save them. You can't just say show, like you normally would on your local computer. This doesn't do anything. Sage knows that any images saved in its worksheet, it will display them. So if you have any way of generating an image that you want to show, if you save it within the code, it will show up in the worksheet.
Hey Ryan, can I ask a question?
Yeah.
Is this included in the help document that's up there? And if not, can you include it in there, this matplotlib stuff?
I can include it. Part of it's already included by accident, sort of. This documentation, it's matplotlib's plot documentation. So it's there. The only thing that's not documented is that Sage requires you to save the image, and I'll put something up about that.
Okay, cool.
Right,
Thanks.
so we can add the demo you just gave to the end of that helper.
Yeah. I'll publish a new version of it.
Yeah.
What also will do libraries, Python libraries, and what
Yeah.
alias has.
Yeah.
There's a lot of libraries available to you. Mostly up to date. Most of them are included with Sage. A couple of them I added myself because they're prerequisites for other code we were using. But if you want,
It's mainly just what is the aliasing.
Right, we'll show you, and what we're going to try to do, and feel free to complain if we don't. Our goal is to shield you from that for now. So we'll be providing these helper worksheets that will kind of encapsulate it, and mostly, the idea is for you to focus on the dynamics and not worry about the programming. So in an exercise, you're mostly going to be asked to just sort of copy some of this helper code over. It's kind of a cut and paste thing, because I really just want you to focus on the behaviors and the fixed points and calculations and things. Now, we'll probably slip up a little bit, so feel free to ask questions and we'll come back and clarify those. Put in some more documentation, that kind of thing. Certainly as we first get started, there's a lot of stuff I realized to kind of get going. So whether we do a good job encapsulating or not, you just have to play it by ear.
so when you go to edit your first homework with the helper code, and you go to publish, click on this worksheet, and edit. You don't see the helper code we added. Right now it's hidden. I'm going to show it real quick. So there's actually this big block of helper code at the top that defines this phase portrait function that we used earlier. and a method of finding fixed points. Yeah, this is used by this. So we provide two functions really, base portrait and fixed points. This one will find the fixed points of a function as a line. You'll see how to use it, and so on. So as you go through here, if you want to look at these this helper code, you'll click Edit, and there'll be a line right here that says hide all. % hide all. If you delete that, as in just delete it and save changes, delete, save changes, this big block of code is right here. If it's in there, so
Right, we tend to put this at the top of the worksheet. It gets executed when you first read the
it's
worksheet
not
out.
here. So you can take on faith that it's there doing its job behind the scenes. And we gotta get through these a little bit. So for example, we'll tell you to use the fixed points function to compute the fixed points between -5 and 5 for whatever particular function this is. We tell you how to call it right here. Function, parameter, blah, blah. And then you can just fill in the blanks here. You will type FPS equals fixed points and put in whatever function you defined, the parameter you defined, the variable you defined, and so on. And then it will plot it for you. So if you have any trouble with that, I mean, Karan and I have office hours, 3 o'clock on Monday, I think. So if this gets confusing, just drop by and we're there to help out. This also might be spruced up a little before you check it out, so it'll have more documentation available for you. I guess that's about it.
Mhm.
So once you do have your homework all finished, so you've got these plots available, for example, the vector fields and such, what you'll do is you'll go up here to File and click Save Worksheet to a File. You give it a name and it saves it to wherever your default save directory is. And then you'll email that file, which will have an extension SWS for Sage Worksheet. You email that to, I guess, me.
Yeah.
And my email address is given on the course website and many times on the front here. So that's a mail to link right there, as is this and this. So you can get those, and there's also links to some documentation here if you log out. So well, you won't need this documentation until next quarter probably, but Sage documentation tutorial is here, and this is on the main Sage documentation website, so you can just go here, read thematic tutorials, linear programming, group theory. So if you're really into group theory, this will show you how to do it. And they have very detailed documentation in the reference manual.
Main tutorial. First one.
Yeah. So you can do animated plots and such if you really want to. They describe how to do that in here. Sage is quite a capable system. It has a lot built into it. So if there's anything you want to do, Sage can probably do it. Just do a search on here, or what is that website? I think. Let's see what's here. Yes. So if you go to the main Sage website, sagemap.org, there's this link right here under documentation. It says ask. This is like Stack Overflow, but just for Sage. So you can ask any question you want there. The developers are very active on there, and all kinds of knowledgeable people. So they can help you with all kinds of things. If for some reason I can't, or Corrado, or the regular documentation doesn't help. Ask Sage is the place to go. Alrighty.
Great, thanks. So I urge you to go check out your accounts today. Don't do it on the weekend when we may not be available. It's just to get you all up and running and start playing around and ask questions. It'll take a few tries. It seems kind of confusing. Like I said on the first day, computing still is an oral culture. So ask questions, send emails, and also you can work together on homework. Send in your own work, but feel free to get together in groups and work on homework. It's just the best way to learn this. So we're going to shift gears a little bit, but I want to finish up something, part of our kind of discussion last Tuesday on different kinds of behaviors. In particular, remember, we went through kind of increasing dimension, 1 dimension, 2 dimension, 3 dimension, at each point asking what kinds of behavior can you get. Fixed points only in 1 dimension, fixed points and limit cycles in 2 dimension, and then all hell breaks loose in 3 dimensions because we have 2 more things, these torus attractors and chaotic attractors. And I ended with some static pictures of the Lorenz and Brüsseler solution sets. Well, and I very quickly kind of waved my hands about how we should think about the shape of them. So I want to show you, and I'll be doing this pretty regularly in the lectures, some interactive demos to help develop our visual intuition. Okay, so I have to do this. So looking at the screen, type in. I'll try to show you what I'm doing here. Doesn't quite fit. It's one of the problems with some of the graphics we generate, right? We have these nice high-resolution desktops, but old video projectors that do very coarse resolution. So I'm a little bit dubious about how this is going to come across at Berkeley and through the camcorder. So if it's not too convincing, if it's too washed out, I might be able to make some movies and then add those back into the online video. Of course, this requires me becoming a better video editor than I currently am. Anyway, so what I have here is a terminal window and then a display window. And the display window will have the solutions of these 2 different sets of differential equations. So the first one I'm going to look at is our favorite, the Lorenz. Standard values, set parameter values. I'm going to keep the time step the same, and then just pick some short. We're going to look at this in 3 dimensions. They're different. This program lets you do different kinds of projections. There we go. Now I'm going to increase the solution. Okay, so what you should be seeing, and I'll be explicit in my descriptions so that you know what you're missing in Berkeley. So we have 2 axes here. They're blue, maybe a little too thin, and over here a little cycle. I just integrated the equation for a little bit, but now I'm going to increase the number of steps from just a few dozen to 5,000 steps. And then what we'll see is now this sort of yellow, brownish, single solution. Now there's a problem here, right? The machines are so fast, it just sort of threw this up here, so it didn't give you any sense of what was going on. What was going on is I put in an initial condition, and the numerical integrator calculated next states and then plotted this out. So you didn't get to see that. I should put in some speed control so we can see it going slowly. Take my word for it. This is a single solution starting from 1 initial condition, and then it traces out this sort of complicated-looking set, complicated trajectory or orbit. But the question is, what's going on? So what I want to do now is kind of fly around a little bit to give you some sense that these complicated solutions have, well, they're not a complete tangle of yarn. There's a certain amount of geometry to them. And to a large extent, what we're trying to do is understand this geometry, this sort of emergent larger shape. Right? The differential equations just say, if I'm in this state, go to this next state. When we look at the solution set, this is really a much larger scale geometry that's emerged from following these local rules. And this larger scale geometry it's determined by the differential equations, of course, but you can't read it off of these local rule specifications, which are the differential equations. So, so now I'm going to rotate the axes around here, kind of up at the canonical position, and then rotate about the z-axis. So hopefully, as soon as I start doing this, our visual perception immediately starts to give us a sense of an object that has some geometry to it. Is this coming through on the video at all, Ryan?
Up here it is.
Okay.
Yeah, it looks pretty good actually,
Oh,
especially
great.
when you zoom in.
Well, that's good. So we can even kind of move around faster. Kind of depends on. Okay, so what are we seeing here? Well, if I go over to this perspective, it's pretty thin. So those big ears look like they're sort of sheet-like. If I look at this way, that was the picture I showed on the last lecture. So the way you should be thinking about this is that out here, we have sort of flat sheets of parallel trajectories, and then they sort of meet somehow, somewhere along the z-axis. There's these two sheets. Imagine if these trajectories here were, say, coming out in the positive direction from the screen, then the other side, imagine that that sheet is behind the screen, and somehow they get sutured together down here. So that's sort of the goal. What is this, what I called last time the branched manifold, the sort of approximate manifold of this? And you can start to get some sense, when you look at the side, how these things sort of come in down here. They don't meet till sort of low z values near the origin. And I can also rotate it around this way. Now maybe this, you start to get some sense of how they suture together. Now, I have to say one thing. I'm driving, right? So, and there's an extra level of feedback I get as I'm doing this that makes the visual object clear. So we'll try to put up some 3D solvers and 3D displayers within the Sage notebook. There's a little bit of security issue with the Java system, but we'll do our best. So you can also drive around. There's no better way to learn about these things than to look at it yourself. I mean, you're getting most of the correct, the visual impressions here, but it's much better that you do the interaction. So you can kind of see, rotate this around.
Hey, Jim, can I ask another question?
Yeah.
It seems like on this system, it's spending, the states are spending more time in the right-hand side at the moment, the way you've got it sort of pictured. Is that because of an initial condition, or if you ran this for many initial conditions, would that still be true? Or as you trace time to infinity, do you think it would spend equal amount of time in each sort of part of that?
Right, okay, so Chris's question was, it seems like it's spending sort of more time over here than here. And is that just due to the particular initial condition and solution, or would that balance out if I looked at a longer trajectory? So if you remember, when I first introduced the equations, at the bottom I noted that there was a symmetry in the equations that you can check. If x goes to minus x and y goes to minus y. That symmetry in x and y means that the distribution will have to be uniform. So if there's any variation from uniform distribution, it's due to the particular initial condition and how long they ran it. So in fact, if you let it go for a longer period of time, it'll fill out. Exactly. So we'll just do that. Right. Yeah. So it looks like it spent more time over here. You can kind of see what's going on. What happens is, again, it's more discussion of the geometry, so you have to develop some visual intuition here. If I come down along the z-axis here and I go way They're following longer and longer. Eventually, I deviate and start going off on positive X or Y. I go way, way out, and that injects me very close in to this, it's called elliptic fixed point over here. It's mostly circular because complex eigenvalues around here. So what happened here, in fact, it may have been where I started it off, it spent a lot of time just spiraling out like this. So it looks like it spent a lot of time there. And I can just change that. Let's see. I'll just do another 5,000 steps. We can see what it looks like. So the first thing, we'll just overlay it. So you can sort of see it's maybe a little more balanced. Now I'm going to clear the previous 5,000 steps. And you can see it's a little more balanced here. Or I can, why not? Let's do 50,000 steps. There. So if you run it long enough, almost a uniform density across the sheets wherever you are. Now there are two sheets here, so in the projection it looked like it's a little more probable, but it's not. So the density here is almost uniform. Kind of tails off a little bit near the center, near the inside of one of these racetracks and near the outside, but it's pretty much uniform. And we'll study this in detail more. How we can understand the probability distribution that's produced by these trajectories. And that's one of the main questions. Here I am talking about probability distributions, the likelihood I'm going to be here in the attractor. But I gave you the deterministic differential equations. So how did determinism lead to apparent randomness? That's one of the main themes here. Well, this is a classic example. So we've already seen what's going on, but we want to understand this in some more detail. How do we understand it? The distribution gets produced by a single trajectory. Okay, so let's go do the same thing for the Rössler. Standard parameter values, don't change the time step. We'll look at it 3 dimensions again. Okay, so this is the Rössler. We're actually looking edge on, so this is the XY plane here, and then this is the Z-axis. So what's happening, actually, there's a large part of the attractor almost can't see because it's actually right exactly in the XY plane. I'll show that to you. See? So it's rotating around the Z-axis like this, mostly flat in the XY plane, and then when it gets to this one quadrant over here, what happens is that the Z coordinate goes unstable. So if I remember, the Z dot equation was Z dot is equal to some constant B plus some constant control parameter C times X, sorry, Z times the quantity X minus C, which is a control parameter. What happens, X is changing signs, which is turning the Z equation stable or unstable, exponentially stable or unstable. So it's stable over here because of the X values. And then this one quadrant, it goes unstable. But the whole time it's going unstable, it's also rotating around and eventually shuts itself down again. So you can kind of convince yourself a little bit by looking at the equations that at least what we're seeing here in the solution set structure is consistent with that. It's not something you can sort of directly derive that would have this shape. But this was sort of shape that Otto Rössler is trying to go for in his personal strange attractor design methodology. So we can also rotate about the Z-axis, get some sense of what's going on here. So very flat in XY. In fact, there's a certain amount of ambiguity in it. Let's see how. Right, so the way we're going to think about this, and we'll come back to study the geometry and describe this quote branch manifold. We have this flat racetrack, and then it goes unstable in the Z-coordinate, and then folds back onto itself. So you kind of imagine this rubber sheet geometry. The sheet if you were flying along inside the sheet and you looked at your neighbors, what you'd see is everyone is moving away from you. Remember, that was sort of the goal. We want recurrent instability. So everywhere in the sheet, your neighboring trajectories are all moving away from you. You start at some point and you do some little perturbation, so those neighboring trajectories, those are always moving away from us. But this is supposed to be stable and recurrent. So we need, it's not just a flow that goes off to infinity, we have to somehow have it fold back onto itself and reconnect. So this is constantly happening. So there's this interesting local instability, separation, small little variations getting amplified. And there's this global geometry which keeps it compact. Right? If we start out in far away from the origin in the three-dimensional flow, all the arrows are pointing in. So from, for some distance, this little attractor down in the origin, it looks like a fixed point. So the flow comes in, and once we get down here, we see that it's kind of stable on the outside, but within it, it's constant, recurrent. States are close passes by each other, and then neighboring perturbations are always being amplified. Okay, just to give us a little taste. So the shifting gears, though, what we're going to do is, in this survey, the main ideas of dynamical systems is I want to talk about how these behaviors change as a function of the control parameters. So this is the area of bifurcation theory. So what we've done so far is just focus in some way on single dynamical systems, certain kinds of invariant sets, fixed point limit cycles, quasi-periodic attractors, chaotic attractors. And now I want to ask, how do those change? In fact, how does the whole attractor basin portrait change as I vary some parameter that modifies the vector field? You could think of this like experimental controls. I have some fluid and temperature difference across the fluid layer. I have convection rolls, and then they might go unstable. So think about these various coefficients in, say, for example, like the Rissler, we had A, B, and C. Those are controls. We ask how this behavior changes. Okay. So last time we were thinking about, I'm going to give you a dynamical system, and you wanted the big picture, the attractor basin portrait. So today we're going to talk about the big picture. How are we going to think, in the style of qualitative dynamics, about how system behaviors can change as we modify them, as we change some control parameter? So we're going to kind of up the level of abstraction, and then we'll come back to some examples. But here's the main idea. I want you to think of, this is purely formal, I want you to think about the space of all dynamical systems. So fix the dimension. Say we're thinking about three-dimensional systems just like the Rissler and Lorentz. So, and they're all specified either by maybe some equations or in the general case just vector fields. So now I want you to think, when I say the space of all dynamical systems over a three-dimensional state space, you're supposed to imagine space of all vector fields I could put down. Okay, so here's my artist conception, because that's not really something you visualize, right? That would be an infinite dimensional space. I could put arrows any possible way at every point in three-dimensional space. But just kind of abstractly, this cube here is the space of all vector fields, and a point is going to be a particular vector field or a particular dynamical system. Okay? So how are we going to imagine changing control parameters? Well, say I'm varying the A, B, or C parameter in the Rissler system. We're going to imagine that we have our dynamical system, and then there's some sort of formal control parameter. Imagine it's just some real number, like A, B, or C in the Rissler system. And so, as I slowly vary that control parameter, the picture we have of what's going on in the space of all vector fields, the space of all dynamical systems, is that we're tracing out a one-parameter family of dynamical systems. Okay, so it's just an arc in this space. And we're interested, as we change this parameter, in how behavior gets modified. So this is the arena of bifurcation theory. So what we're going to say is that as we vary this parameter along this arc, if behavior changes qualitatively. We're going to say that there's a bifurcation. So say on this side I have a single fixed point, and on this I have 2 fixed points. There's no way for me to sort of rubber sheet distort the state space to change that number. Now maybe, sort of before this bifurcation happens and I'm varying the control parameter mu, maybe the fixed point is moving around. But I'm allowed, under this notion of qualitative equivalence, to do a rubber sheet distortion. But as soon as I change the number of fixed points, or the fixed point turns into a limit cycle, there's a qualitative change, and those behaviors can't be mapped into each other. Then we say at that parameter value mu, where that change occurs, we've had a bifurcation. So the definition of bifurcation is a qualitative change in behavior as you slowly vary a parameter. Now the caveat here on slow, it's a little bit familiar. People who study physics, we have words like adiabatic and quasi-static change of parameters. And thermodynamics, meaning we're always kind of staying in equilibrium. It's kind of the same notion here. If I vary the parameter too fast, I'm actually adding some dynamics to the system. So here, when we're talking about bifurcations, the variation of the control parameter is just arbitrarily slow. So we're always seeing a single dynamical system. It's not remembering it's a previous setting, previous behavior or state. And then, so now the sort of one of the main questions in bifurcation theory is, is there some organization in the space of dynamical systems to where these bifurcations can occur? So what I've kind of done here is this little light blue sort of to indicate kind of sheet. And you can kind of imagine that even if I changed how I varied the parameter and went through and punctured the sheet different ways, I'd still have the same bifurcation going on. So the question is there some way of classifying how these bifurcations can occur? What kind of bifurcations are there? And then how does that organize the space of all dynamical systems? Maybe somewhat surprising, we'll talk about this. There's actually quite a bit of structure. So not only are individual dynamical systems structured in terms of invariant sets and how those are stable or unstable, attractor-based and portraits, separate matrices based on attraction, but even at the level of how they can change in behavior, there are a number of constraints. And so we'll be able to classify how behaviors can change. Okay, so that's the sort of the very general motivation and picture behind this. And so what I want to do is go through some one-dimensional examples to give you a kind of flavor of the kinds of qualitative analyses you can do that give you some sense of possible changes in behavior. And so today, we're going to focus on just equilibrium fixed points. Next lecture, we'll talk about how time-dependent behaviors, fixed points go into limit cycles, how limit cycles can change in limit cycles, and how limit cycles can become chaotic. Today, just to get started, mostly to help visual intuition, we're going to just look at how fixed points can change, their stability and number. Okay, so 3 kind of classic simple examples. So the first one is called the saddle node bifurcation scheme, or more picturesquely, the blue sky catastrophe. The notion of catastrophe will be why that's used to become clear, including why blue sky. Now, in the theory of bifurcations, there are sort of prototype differential equations that sort of encapsulate these different kinds of bifurcation. And in the terminology of the area, those are called normal forms. You can sort of show if the system is going through one of these so-called saddle node bifurcations, this very simple one-dimensional differential equation captures all of the essential features. And this is simple. It's just x dot is equal to r minus x squared. So just a constant minus x squared. And it's set up so that the bifurcation occurs when r goes to 0. So let's do the same kind of plot we've done in a couple lectures already. So when r is negative, just look up here. Well, x squared is always positive, therefore negative x squared is always negative. If r is negative, everything is negative. Therefore, the vector is always pointing to negative x, right? X dot is negative, therefore the vector field points down this way. So again, I'm plotting the state space, one-dimensional state space, and then basically f of x on the right-hand side, or x dot this way. So we have a parabola here that's just offset by a constant control parameter. So it's just, in the general case, looks like this. So the green here is just f of x, the right-hand side, and it's below x dot equal to 0. That means that Right? Each value here says that's the strength of the vector, and it's always negative, so it's always pointing this way. So wherever you start, you're going to go off to minus infinity. Okay. So then, you take x right up to x, or r right up to 0. What happens, that's of course changing this parabola offset, and it finally exactly touches x dot is equal to 0, which is where you have a fixed point. So this is the birth of a fixed point. No fixed points here, right? No matter where you start, you're going to flow off to minus infinity. Nothing stationary. But here, right, r equal to 0, we get a fixed point. And in fact, you can kind of tell from this, again, the green part of the function is always negative. So what we get for this fixed point is mixed stability. If I start on the right side, positive x, it's going to come down and stop. If I'm at x0, x dot's equal to 0, I'm going to sit there. If I perturb just a little bit off and started at negative x, it's going to flow off this way. So things kind of flow in and stop at the origin, or if you start negatively, they flow off this way. Okay, so neutral stability. Okay, so now let's increase r to be positive. What happens is this quadratic function punctures through the x-axis. Now we have a portion of f of x, the vector field, right-hand side, that's positive, which means the arrows are pointing this way. But you kind of see what happened, right? Now I have two places where x dot's equal to 0. One, again, graphically, you can appreciate that. It's a fixed point, but it's unstable. I start up here, I flow away from it, I start negative, I flow away, but this one is stable. So it kind of came across, there's this one particular r value, r equals 0, where we first got a fixed point. There's mixed stability. In some sense, that mixed stability can split, and we had the birth of two separate fixed points, one unstable and one stable. Okay, so now these are kind of like these are snapshots of the state space, the vector field, at different particular r values. But we're trying to think about what's the structure in the space of all dynamical systems. So that brings us to what's called a bifurcation diagram. So we kind of step back. And what we're going to do is just plot the fixed points, not the whole vector field, but just the fixed points as a function of the control parameter. Right? So here is my state space, and it's one-dimensional. And then here's R. So generally, a bifurcation diagram is we plot the attractors and repellers as a function of control parameter. And what we get here is, remember, if R is negative, there's nothing. We just flow off. There's nothing to plot it. Right at R equal to 0, the origin is marginally stable, half unstable, and then we get this splitting off of a stable fixed point, which I draw with a solid line, and an unstable fixed point with a dashed line. So that's why it's called a blue sky catastrophe. In fact, if you had a complicated set of equations and you were varying some parameter, oh, there are no fixed points, and all of a sudden, boom, this just appears out of nowhere. In fact, because the equations are so simple, remember, x dot is equal to r minus x squared. We're plotting where x dot is equal to 0, so I can solve for x star, the fixed point, as a function of r. Well, it's a square root of r, so I put down here we have two branches. Just looking at this equation, setting this equal to 0, I can solve the x values that make that 0, and it's plotted now as a function of r. And that's why we know it has that kind of parabolic shape. So no fixed points, now two fixed points. So one interesting thing about this class of bifurcations is that we can think about the fixed points and their stability as if these are charged particles. And when you go through one of these bifurcations, charge is conserved. Now, this is just a little bit of a helpful fiction, right? So when r is negative, what's the charge? It was 0. There's nothing there. R is positive. What's the charge? We have stable fixed point, unstable fixed point. Charge of 1, charge of minus 1, total charge 0. So these are kind of local bifurcations. We're sort of looking at small values of r right around where the bifurcation occurs. Okay, so saddle node bifurcation, kind of the first one. The next kind of bifurcation is called transcritical bifurcation, or prosy way, exchange of stability. And we'll see why when we do the bifurcation diagram why that's the case. The normal form for this bifurcation is actually not so different. X dot is equal to r times x minus x squared. So all I did is add an x right next to the r, 4. Now, looking at the right-hand side, we know that for all r values, since x occurs in both terms, that the origin is going to be a fixed point. X equals 0, x dot sub is going to be 0. So that's always going to be there. Now, graphically, what's going on, and it's a little more work to think about why. So when r is negative, well, in all r values, the origin is going to be a fixed point. So we know whatever this function is here, it's got to pass through the origin. So when r is negative, what happens is that there's a small segment in here, just below the origin, where the vector field is positive. Right? There'll be so here, this is the negative x-axis. R is negative, so r times x is positive, and if I'm sufficiently close to the origin, x squared will be small. So this first term will dominate and be positive. So I know that there's some part of the vector field, the right-hand side is positive, and the vector field is pointing this way. So I have this pair of fixed points, one at the origin. This one's stable by this analysis. Still connected. Last time. And there's another one over here, which we can solve for, of course, where it's unstable. Then, when r is equal to 0, we're actually sort of back in the same situation we were with the saddle node, except we're passing through space of dynamics in a slightly different arc. And then when r goes positive, we have the mere symmetric situation. We can actually tell that this function has that symmetry. So as soon as we've analyzed this, we know that exactly complementary picture is going to happen over here. We have now the origin has gone unstable, and then we have a positive, a stable fixed point of positive x. Okay. So any guesses as to what the bifurcation diagram is going to look like? Right. Remember, that's plotting these fixed points. Now we have two, except for this one degenerate case at the bifurcation. We have one fixed point there. So you have two fixed points, one fixed point, two fixed points. We actually have to solve this guy for x dot is equal to 0. And we want to solve for x star as a function of r to get it. And, well, we already know one solution, x is equal to 0. That's always got to be there. But what happens is this. So here's the origin, x equals 0. It's always there, it's always fixed point, except here it's stable. Above r equals 0, it's unstable, dashed line. Then we have this other fixed point sort of coming in from negative x. It's almost like a particle interaction. It kind of collides with the stable fixed point coming in, and then it goes off and becomes a stable fixed point. And they're both just linear functions. Why are they linear functions? Well, x dot equal to 0, I already know one of the solutions, x equals to 0, I factor that out, and then I just have to find out where r is equal to x. Okay. So that describes this other thing coming in. And then the description is exchange of stability. It's as if this fixed point and coming in from negative x and the one at the origin, they kind of continue on through each other, but they've exchanged their stabilities. And notice again that this sort of fake, what's called topological charge, is 0 for every r. Right? One fixed point that's stable, one that's unstable, will sum up to 0 for all r. Okay, so these are pretty easy to analyze, just one-dimensional differential equations. Now, so the final one-dimensional example will be, it's called the pitchfork bifurcation, and we're going to see lots of examples of this, well, in this add-on too, later on. It's normal form. Again, it's not that different. It's pretty similar to the exchange of stability bifurcation, except instead of x squared, I have x cubed. Okay, so now we've got this cubic function, and what does it look like? So for negative r, well, again, same argument. Notice x occurs in both terms, therefore the origin will always set x dot equal to 0. So this function has to pass through the origin no matter what the r value is. But then we have this cubic function here that, for negative r and negative x, it becomes positive. Right? So x is negative, you cube it, that's a positive. That's a negative number, but it's minus sign, so that's positive. And then x is negative and r is negative, so this is all positive. So this is always positive over here. when r is negative. When r is equal to 0, we just have pure cubic going through the origin. And then the interesting thing, of course, when r goes positive, one way to think about this is close to the origin, right, the x cubed term is going to be small, and we just have this linear function dominating the vector field. So we have that linear part of f on the right-hand side. And eventually, far enough away, x cubed starts to dominate, and then it pulls that linear function around the origin off to negative x dot and positive x dot. So here we're going from one stable fixed point to 3 fixed points. 2 stable, 1 unstable. And here's the bifurcation diagram. Negative r, just had that, just the origin, and it was stable. Just passed the negative slope of the origin. Then right here we have this birth of 3 fixed points. The origin loses its stability. And we have 2 branches coming off. Just 2 stable fixed points. And again, they have this, the 2 roots of solving for a fixed point, depending square root on r. Okay, so these are very common bifurcations. In fact, when we start playing around solving some of these differential equations, especially around where they're chaotic, you can change the parameter values. You see periodic orbits appear, fixed points appear, some abandoned, and you'll find these kinds of bifurcations are pretty common. Now we know sort of how to analyze them, at least around parameter values close to where the bifurcation occurs. Now it might help a little bit, and this will make a little bit of a connection back to some physics, although this is not a second order system, it's just first order differential equation. But we can think of these one-dimensional differential equations sometimes in terms of a particle evolving in a potential. Well, technically this is a particle moving in molasses in a potential. So if I write down my differential equation, x dot is equal to little f of x, sometimes I can rewrite that f of x as the derivative of a potential function v. Or the other way to say this is this v of x is simply the integral of f of x. Now, why do I mention it? Well, in the case of this pitchfork bifurcation, I have this rx minus x cubed. When I integrate that, I get an x squared term and an x to the 4th term. At least that looks like some kind of superharmonic potential. Again, this isn't a second order system, but you can think about it that way. And this sort of second quadratic potential well is playing off against the 4th order potential well. And as a function of r, it's going to change sign, dominate or not dominate. So the potential well interpretation of this pitchfork bifurcation is following, and maybe it's a little more intuitive. So for r negative, I had just a pure convex, upwards convex potential. And if I imagine this particle rolling down very slowly, it's in molasses, there's no second order term. No x double dot here. It would eventually settle down here and stop, and that would be the fixed point. Write it r equal to 0, well that turns off the quadratic term. So this is just x to the 4th. It's a very, very flat potential. You can kind of imagine. The ball comes down, it kind of rolls around a little bit, it's so flat. But then, when r is positive, what happens is this square potential turns over, it's unstable. So near the origin, right, the x to the 4th term goes away. We just have this, but now it's negative. Far enough away, the x to the 4th dominates and the potential increases again. So we get 2 potential wells. So an unstable maximum, the origin, and then 2 stable minimum, the corresponding fixed points. Okay, sometimes that's helpful to think about this pitchfork bifurcation. It's again, very common. We'll study this in some detail. We talk about cascades of bifurcations. So this has all been sort of local, small values of the parameter right around where the bifurcation occurs, and the fixed points vary continuously with that small variation. Now, other more interesting things can happen. And that takes us to what are called catastrophes. So we're still talking about how fixed points can change the fixed points. But with catastrophes, what happens is that fixed points can just disappear, and the system will just hop to one very, very far away. Not that there's some small, square root dependence closeness notion. There can be huge changes suddenly as you very slowly vary a parameter. So this sort of popularized in the 60s by the French mathematician René Thom, called catastrophe theory, and it's sort of a model of sudden change. Even though I am only slowly changing the control parameters on my experiment, there's nothing that I'm doing that's going to cause it, and suddenly, boom, the equilibrium that you were at just disappears, and the system flops into some completely different attractor. Which idea is finally taking hold in the world of climate change. So this might come off as just a mathematical analysis, but some of these paradigms of change inform how we think about climate change and the weather and so on. This notion that the equilibria change only slowly as we change a control parameter, that corresponds to these pictures we've all seen of mean temperature change between 1900 and the year 2100. And we dump in more carbon, and there's this proportionate change, 2, 3, 4, 5 degrees C as we go further out. And the big error bars there. Could happen that way, but actually the weather, it's hydrodynamics. At least it's more than hydrodynamics. It's at least hydrodynamics. It's a very nonlinear system. And we can have some of these catastrophic changes. Just because I'm slowly dumping more and more CO2 in the atmosphere, you can have these sudden climate shifts, is the idea. Sudden climate change. Suddenly, other mechanisms come in, get activated, that change the available equilibrium. This, to me, is the most frightening thing, because we don't know what can happen. The weather system is extremely high-dimensional, not like these very low-dimensional systems where we're going to classify what can happen. But even here, we can see that there can be these sudden changes. So I'll go through just one example of this, how it works, and it's actually going to lead us to think a little bit about doing some computing with nonlinear systems. Okay, so what I'm going to do here, and this is just one example, it's called the cusp catastrophe. And it starts off with the pitchfork bifurcation normal form, Rx minus x cubed, except I'm going to add another control parameter. So this is a catastrophe where I have the R control parameter and then just a constant offset h. And we can also think of, this actually as being some kind of potential here, where, kind of physics terminology, this would be an external field. But the analogy kind of breaks down. It's not that good for these transitions. Anyway, we already did all this, right? With h equal to 0, that is the pitchfork bifurcation. So if we were just looking at the bifurcation diagram, we have our pitchfork bifurcation. Origin goes unstable, and then this square root of r set a fixed point coming off of it. Now, when h isn't equal to 0, when it's positive, what happens is, an appeal to your intuition here, the vector field has a little positive component, so it kind of breaks this three-way intersection so that the fixed point down here for negative r, it stays on its own branch. And then what's left over is a saddle node bifurcation. And you can go convince yourself that the arguments we've introduced already. If I make h a little bit positive, I can go solve for the x stars that makes x not equal to 0. You can convince yourself that you have this type of, now I just have the fixed point near the origin. It just shifts a little bit as a function of r. And then some finite distance away, not arbitrarily, but some finite distance away, a pair of fixed points is born. Okay, now the exercise here that we have to do is imagine these bifurcation diagrams as a function of h. I'm showing them as a function of r at two different r values, at two different h values. And now I want you to imagine that in the third dimension here, I'd stack this up. Here's h equals 0, here's h positive. And you have to imagine this blue lines, they actually form a surface. And the result is this. So what I'm showing you here is, first of all, this is the control space. I'm the experimenter. I get to choose R value and H value. And then in this third axis, I'm plotting where the fixed points can be. Okay, so now as a function of R, if I set H equal to 0, which would be this line, I didn't add it in because the plot's going to get kind of busy. That corresponds up here to having a single fixed point. And then you have to kind of imagine the way I've drawn this curvy surface, that two branches, stable branches, come off of it. And then there's an intermediate sheet that's unstable. Right? So if I took a vertical slice, again, I have trouble here with my artist conception, but if I took a vertical slice right at H equals 0, and I looked at the intersection of that vertical slice and the blue surface, we call the behavior surface, that would be exactly the pitchfork bifurcation. Then that positive H value, like I said before, that was, remember, if I was increasing R, oh, there's just a little bit of shift of the position of the fixed point at the origin, and then down below, there's a slice here that cuts through here, I would have an unstable and a stable branch, a saddlement bifurcation. Okay, so you have to ponder this a little bit. But so the vertical slices were before the kind of bifurcation we're dealing with. Now we want to think of that as a surface. Or just to say, more directly, over the control space, we have a two-dimensional control space, I want to plot all possible fixed points, stable or unstable. And for that classical catastrophe, one-dimensional differential equation, this is the shape of object you get for where the fixed points can be. The upper and lower surfaces are stable, and the intermediate ones are unstable. So these correspond to, say, minimum of the potential or stable fixed points, and then right along the x-axis, we've gone from stable fixed point at the origin to an unstable fixed point at the origin. Maximum potential. What that means is, again, I'm just kind of reinforcing the geometry you should see in this cartoon picture. Out here, outside this red curve, red area, outside here, like all those are H pairs. If I look up, I'm just going to see one fixed point. And then there's going to be some region inside here where, for those RH values, I look up and there'll be three possible fixed points. Two stable, one unstable. Now, where does this boundary come from? It actually is the projection of this edge, just right where the surface folds over itself, right where the surface folds up. That's exactly where the number of equilibria changes. And so I'm plotting here this red curve, cusp, that's cusp catastrophe. This cusp down in the control space is where the number of solutions changes. And it changes abruptly. So we call this the bifurcation set. So think back to that first picture, kind of abstract picture. We have this question. Space of all dynamical systems, an arc as I varied a parameter, and there's this sort of surface that you go through, and you have a bifurcation. This is the kind of first picture of what can happen. I can sort of drive around. I'm the controller. I can drive an RH space, and when I cross this, suddenly I'm going to get three solutions. I go from one solution to three solutions. Okay, let's do that. So what we're going to do is agree to do an experiment where I perform a series of manipulations so that in the control parameter space, I just do a loop like this, so clockwise, if you will. Notice that out here, I have one solution, one solution, one solution, one solution. But right here, it corresponds to being on the upper surface. So if I keep going, that's fine. I still just have one solution, and I don't know that way over there in the state space, something else is going on, the potential for these other fixed points that occur, because I'm still up here. But notice when I come over to this edge of the bifurcation set, right at that value, suddenly I'm at the edge of the surface. And if I move R any further, I only now have one stable fixed point I can go to, but that's on the lower branch, the lower part of the surface. So I get this huge jump in equilibrium. So every time I go around here, so I go up here, everything's kind of, the fixed point locations are slowly changing, and kind of proportional to how I'm varying R and H. And then suddenly I get to here, unbeknownst to me, I change R and H by an epsilon, boom, I get this sort of macroscopic movement in the state space to a completely different equilibrium. Well, we can do the complementary experiment. I can go around counterclockwise. So I'm traveling up here on the surface again, the fixed point's just changing its position, that's fine, all proportional, until I come along the lower sheet here, and suddenly there's no place for me to go. Right? The unstable fixed point, stable fixed point sort of come and annihilate each other, and the only place I can go is back up to this upper sheet to the stable fixed point. Again, sort of macroscopic change in equilibrium. So that happens over here in this other branch of the bifurcation surface. So this is interesting. Technologically interesting. Because I have a system whose current stable state depends on the path I took in the control space to get there. That's called hysteresis. And this led to part of the computer revolution. Because this system, I can drive it around and store it in this state or this state, as in the 1 state or the 0 state. So this was actually used in the first, and I'm probably dating myself here, in the first magnetic computer memories. They had little magnetic cores, and you could polarize, or they should magnetize the core to be clockwise or counterclockwise. And you did that by pulsing currents in different directions to drive in one state. And once you turned the currents off, it was stable and would sit here. And the very distance between these two different stable states was extremely important because you didn't want noise or turning the power on or off or any perturbations to destroy the memory. This is really handy. Back when I first started programming, we had mini computers with core memory, and you could trip over the power cord, plug it back in, and keep computing. Wouldn't lose a beat. Of course, that was the 70s. Then we went through the dynamic memory phase, which if you turned the power off or lost your battery, you lost everything. Now we're back with solid state memories too. Storing things permanently. Anyway, so this is actually the kind of first indication of how nonlinear systems, a real simple system in this case, can store a bit of information. A theme that you keep coming back to. So that's just one example, and it turns out René Thom, the French mathematician in the 60s, and some Russian colleagues, Soviet colleagues, fleshed out a rather detailed classification scheme. Remember, this is sort of my favorite thing about dynamical systems. Again, without solving in detail these equations, we're starting to get some sense of, before it was what kind of behaviors can there be, and now, how can those behaviors change? There's actually a classification scheme. So if we're interested in how equilibria can change into other equilibria, there's a classification scheme that goes under the heading of either catastrophe theory, sometimes you'll see it called singularity theory. But anyway, and there's this table sort of indicates some of the results. I won't go in detail into this, but there are whole books on this quite interesting theory to work through. So we have a control space and the behavior space. So by controls, we have one control that would be just like R in the 3 first bifurcation schemes we talked about. The cusp catastrophe has 2 controls, R and H. When I'm talking about one behavior, 2 behaviors, so one behavior, this is the dimension of the state space. So just one-dimensional differential equations here. But there's also a classification scheme for 2-dimensional dynamical systems, vector fields and continuum. So we went through the fold or saddle node bifurcation, 1 dimension state space, 1 control, and then we sort of generalize that to the cusp catastrophe, 2 controls, R and H, and it kind of goes on. And they were not short on cleverness of names for these different surfaces. 3 controls, 1-dimensional differential equations, we have swallowtail, butterfly behavior surfaces, and so on. In 2-dimensional system, hyperbolic, elliptic, and parabolic and bilic surfaces, and so on. Quite picturesque. So here's kind of a rogues gallery of some of these things. So the swallowtail catastrophe, again, we have 1 behavior, so we're just looking at 1-dimensional differential equations with 3 controls. Now, this might sound a little bit strange. I mean, here you are in your lab, and you've got 3 controls you're changing. So this is to see this, you have to be manipulating things sort of simultaneously. So it's a little bit maybe impractical, but people have found these. So here's the behavior surface and projecting down here now in blue. This is the bifurcation curve here, hence the name swallowtail. And it gets a little harder to kind of visualize how these surfaces fold over each other. And this is where 2D or even 3D projected graphics doesn't help. You really need to play with these things. For those that have Macs, I have some very simple code that will plot these out. You can locate them around a Mac application called Grapher. I haven't done this in Sage yet, but it would be a nice project. One behavior and 4 controls. Butterfly, kind of not very well rendered here, but this is complicated control surface. Again, as you're moving around in the control space, all these little curves, I mean, the number of solutions is changing very rapidly. And then this is, well, we have problems visualizing this. So the elliptic umbilic catastrophe is 2-dimensional vector field, differential equations, and 3 controls. So that's a 5-dimensional space. So here what we're showing is just a projection down through the bifurcation surface, and forgetting the controls. So this is just forgetting these are, okay, this space, the surface are the points in the 3-dimensional control space where the number of solutions changes. So I'm not plotting the behavior space, the behavior axis at all. Now the interesting thing about this classification scheme, notice down here, 5 controls, even in 1-dimensional system, and by implication 2-dimensional systems, you can show there is no finite classification. And what that means is that for these systems, in kind of generic case, this is done in kind of topological generality. In this case, as you're varying, okay, I have 4 appendages, so 4 controls, and someone else is twiddling another knob in the experiment. This 5-dimensional control space, as I'm moving around, every epsilon change in the control parameter, the number of solutions is changing, continuously changing. That's complicated. Well, I'll show you some examples where that actually occurs in lower dimension. We can start looking at some chaotic systems. So that's just talking about bifurcations between equilibria. So next lecture, what I'll do will be a little bit of some analysis, but mostly some simulation examples to get some sense of how time-dependent behaviors, how fixed points can turn into time-dependent behavior like limit cycles, and limit cycles can change into tori and other things like that. So that's it. Any questions? No? Okay. Good. So good luck on the Sage, and again, don't hesitate to ask questions. When you get started, it'll be a bit arbitrary, so just work together.
So,
All right, thanks, Jim.
obviously I don't want to submit